we were God, we merely looked out from on high and we'd say, you're diseased and you're not, because, you know, being God, we know all and we see all. But we're not that good. In order to get a sense of what's going on with the patients, we need help. And the help we invent is a test which classifies people as disease or non-disease, and that's what we use when we go forward. The key idea here, what we're really talking about, is simply this. The test is not always right. The test is not always right. If you assume the test is always correct, you're a bad doctor. There's the test and there's reality. Sometimes there's a lot of agreement between those two. Sometimes there's really not a lot of agreement between those two. And the idea, what we're talking about today, is right here. Folks, if you've ever had trouble with epidemiology or indeed biostatistics, this is why. You think that the test is real. You think the results the test are providing are God-given reality. No, they're man-made guesses of reality. And the idea, the mental ability to understand what the test says and what that relationship is to the actual reality is really what our conversation is. Now, come on, you know in your better moments, we don't perceive reality as people walking around the world. You know from your studies, we take in sensory information, and using that sensory information within our brains, we construct a picture of reality. I'm not being philosophical here, I'm being medical. This is how we work. And so you as a physician are subject to the same. You get information, and the question is always, is it information correct or not? We need to find ways of telling ourselves, how good is this picture of reality? How good is the information we're getting from our test? Because here we go again. If you think the test is always right, you're not my doctor. I'm not coming to see you, and I'm not sending my family to see you. Because why? Because you're naive and you lack the medical sophistication we need you to have. The question is, how well does the classification by the test correspond to, well, what we call the gold standard of reality, however we might measure that? How well does what we have from our test match what reality is? There's a number of ways we can look at this, but by far the simplest, the most obvious, is to construct a simple 2x2 table, which I've done here. Now, this 2x2 table is laid out the way most 2x2 tables are. We have here on the side test results, positive or negative, and we have up here on the top, we have the gold standard, disease or non-disease. But I need to alert you, sometimes on exam questions, they like to rotate the table. They may put disease over here. They may put the actual test results up here on top, or they may switch rows and columns. The first thing you should always do in an exam question is check the format. Make sure that the table is in the standard geography. It's a good thing to miss the question because you just missed the table rotation. So here I have a 2x2 table, and I put numbers in the table. I put 850, 150, 350, and 650, right? But our table's not complete yet, because tables are made up not only of numbers in the cells, they're also made up, and importantly, of something called marginals. Marginals are the sum of the columns and the sum of the rows. And I'm stopping to remind you, marginals are an equally critical part of the 2x2 table. We get the marginals by simple addition. The number of diseased people, 1,000, adding down the column. Number of non-diseased people, which I'll also call the healthy people, adding down the column, 1,000. Number of people with a positive test, we have 1,200. Number of people with a negative test, we have 800. And then we also need the total for the table. What's the total for the table? Well, 2,000. The number either down or across the marginals, but of course not both. Oh, and by the way, what letter do we use to represent the total for the table? The total for the table is represented by the letter N. N is the total for the table. In epidemiology and biostatistics, N means your sample size. N is the number of people that we're dealing with. Now, I know that this is gut review for some of you as I'm doing the 2x2 table, but I want you to start with an understanding of where we get the table before we talk about what to do with the table. We simply get classifications provided by what the test says, what the actual standard of disease is. We construct our simple 2x2 table here. Now, at this point, many texts ask you to go through and label your cells with the letters A, B, C, D, and thus labeled, execute basic calculations for common screening or diagnostic test parameters. Now, many of you know what I'm talking about here: sensitivity, specificity, positive, negative predictive value, and accuracy. These are sometimes called the big five. If you know how to get these figures based on the so-called ABCD method, that's great, that's fine. It'll serve you well in your exam, indeed in the real world, no problems. But folks, if you don't know how to do it by the ABCD method, or you're confused by the ABCD method, listen, never learn it like that. Because in the heat of battle, in the middle of the exam, you quickly forget which cell is A, which one's B, which one's C, which one's D. And bluntly, folks, if you can't remember ABCD, you're screwed, aren't you? So forget ABCD. It's a stupid way to learn it. These cells have, each of these cells has an actual name. Let's call the cells their actual name so we know what we're talking about. All right, look with me here. Everybody in the top row got a positive on the test. Everyone in the top row is a positive. Notice there's no question. Everyone in the top row is a positive. Why? It's what they got on the bloody test. There's no question about it. The test tells you who's positive. In the same way, everyone in the bottom row is a negative. The test defines who's negative. There's no question about positive or negative. It's an empirically given fact. Top row is positive, bottom row is negative. Good. Now we've established that. Now let's ask the question, what's the agreement between what the test says and what the gold standard is? Well, here we have positive test with actual disease. Hey, that's a match. And we call those matches true. The diagonal cell, we have negative with no disease. Hey, that's a match. And so we call that true. The off-diagonal cells, positive with no disease and negative with disease, well, those mismatches we call false. And there you have your true names: true positive, true negative, false positive, and false negative. Folks, when you label your cells, do what I just did. Don't look for the true positives. No, no, no. Look for the positives that are true. Don't look for the false negatives. No, no, no. Look for the negatives that are wrong, ergo false. In other words, reverse the letters. Start with what you know, positive or negative, and then reach for the conclusion, true or false. By saying true positive, we're writing this in the most confusing way possible. Epidemiology does that a lot. It's positives that are true, true positives, negatives that are false, false negatives. Worry about positive and negative first, true or false second. You'll find you make many fewer mental errors. Once again, as a reminder, don't simply walk away going, oh, yeah, doc, I got that. The true positives are in the upper left-hand corner, because I already warned you they can and like to rotate the table on you on the exam, right? You can't just learn this by sheer geography. You have to have a sense of what the labels are and what they mean corresponding to the table. Well, now that we have our table all laid out, the table laid out, cells labeled, the marginals in place, now let's talk about doing some of our basic calculations. The way we're going to decide which test is the best test is by using two calculations, sensitivity and specificity. Sometimes these are referred to by some people as pre-test probabilities. These are the probabilities that are in place before we run the test. These are, in some great sense, the defining numbers for the test. As we'll see going forward, these numbers are fairly constant for each test and always true for that test in almost all situations. How are we going to do these calculations? I'm going to give you one of my favorite rules here. We're going to introduce it now, but use it all the way through. Here's the rule. The calculation is trues on top, divide by everything. I'll say it again, trues on top, divide by everything. You're going to find I don't spend a lot of time teaching formulae. Why? Because in my experience, I teach you the formula today, you forget it by tomorrow. It's not a really good conversation. But if I teach you a rule that lets you get the formula in all situations, you're served in all situations. So here we go. Say it again with me. Trues on top, divide by everything. We call this, surprisingly, the trues on top rule. So, using this rule, trues on top rule, how we're going to calculate sensitivity and specificity. All right, before we can talk about the calculation, we're going to make sure we know what the hell we're talking about. So what is sensitivity? When I'm talking about sensitivity, what am I talking about? Sensitivity is about, here we go, detecting disease. When I have perfect sensitivity, I've detected all the disease. Every diseased person is identified if I have perfect sensitivity. Please notice what I've done with the healthy people is irrelevant because all we're focused on for sensitivity is disease. Disease and nothing but disease. The issue we're looking at is what percent of the diseased people are correctly identified. If we have perfect sensitivity, we get all of them. Formula, trues on top, divide by everything. The true positives divide by true positive plus false positive. Notice sensitivity, we're concerned with disease. So everybody in the calculation for sensitivity is a diseased. What did I just tell you? I just told you that we're going to ignore all the non-diseased people, healthy people, and we're just going to focus on the diseased people. What did I say? Trues on top, divide by everything. Therefore, 850 divided by 1,000, or as you can see, 85% for sensitivity. 850 divided by 1,000, or 85% sensitivity. 85% sensitivity. What is that? Good, bad, or, well, you know what? It's actually not bad. Now, if I didn't have a test and I was just doing a random guess, my guess would be 50-50 in terms of disease versus non-disease, right? So this is a nice improvement over 50% success rate. I'm now at an 85% success rate. Now, some of you are thinking, but wait a minute. I've heard screening tests should be like, you know, numbers like 95 or 99%. Okay, first, stop that. Let's talk real medicine, shall we? Real medicine is not about some arbitrary percentage you memorize. Real medicine is about what else you got. What am I telling you? If this is the only test you had, you would use it, and happily so. Because getting 85% of the diseased people identified is better than a 50-50 guess. Don't you agree? Now, if there was a better test for identifying diseased people, one that gave you 90 or 95%, you would toss this one aside and you use that other test, right? But in medicine, it's not about some magic number. It's about, yeah, what else do you have? And if you have a test that gives you 85% sensitivity, and that's the best thing we have, well, it's certainly not perfection, but you know what? That's a really useful tool because it's moved us a lot farther towards a grip on reality than a 50-50 guess, right? Remember, it's always about that getting the test result and then realizing it's not going to be a perfect representation of reality, but gets us closer to reality, that issue over and over again. Just to draw your attention to something that we sometimes hear about, you may not think about, something called the false negative rate. False negative rate is computed by 1 minus sensitivity. So in this case, that would be, of course, 15%. False negative rate would simply be 150 divided by 1,000. Yes, I know that violates the trues on top rule because the false negative rate is a derivative calculation. It's not the core calculation. Core calculation is sensitivity 850 out of 1,000. Trues on top, divide by everything. Sensitivity is about detecting disease. Specificity, therefore, well, is about identifying the healthy. What's left? When I have perfect specificity, I've correctly identified all the non-diseased people. What about the diseased people? We don't care about them when we're talking specificity. Said differently, everybody in the calculation for, well, I have an error here. Everyone in the calculation for specificity is a non-diseased person. Everyone in the calculation for specificity is a non-diseased person, a healthy person. The issue here is the companion to sensitivity, where sensitivity says what percent of diseased people are correctly identified by the test. Specificity says what percent of the healthy people are correctly identified by the test. Notice these two things are independent. Just because you know how good the test is on sensitivity doesn't mean you know how good the test is on specificity, right? Once again, we apply our rule. You remember the rule. Trues on top, divide by everything. Or if you prefer, that would be the true negatives divided by all the healthy people, because everybody in the calculation for specificity should be a healthy person. Well, let's go back to our friend here, the 2x2 table, shall we? Back to our friend, the 2x2 table. And now we're going to absolutely ignore the column on the left-hand side. That would be the disease column. Don't care about that, because everybody in the calculation of specificity is a non-disease, that is a healthy person. Okay, here we go. Let's apply the rule. What's the rule again? True's on top, divide by everything. In other words, 650 divided by 1,000 gives you the answer of specificity of 65%. Please notice, importantly, the true negatives are in the bottom row. The true positives are in the top row. They're not side by side. They're diagonal with each other, of course. Well, you should also then notice we have another derivative calculation, the false positive rate. The false positive rate is going to be 1 minus specificity, or in this case, 350 divided by 1,000 is going to be the false positive rate. If we have 65 for the specificity, the false positive rate is therefore, of course, going to be 35%. These are linked together. 1 minus specificity gives you the false positive rate. So, given standard way of presenting 2x2 table, the calculations for sensitivity and specificity, these so-called pretest probabilities, are using the columns, the calculations in the columns, the column of disease or the column of non-disease. How do we know which column to deal with? That's easy. We're talking about sensitivity. We're only going to be focusing on disease people. We can ignore all the non-disease. Talk about specificity. We're going to be talking about the healthy people, that is, just the people without the disease. Sensitivity is the ability of the test to identify correctly who the disease people are. Specificity is the ability to identify who the non-disease people are. And these two things are, once again, independent. Just because you have great sensitivity doesn't mean you have terrible specificity. These two things are independent from each other. We simply have a table, remember, that we constructed by getting test results, and we then compare those test results to some gold standard. The way this often works is, well, the test results, these are something that we can get quickly in the clinical setting in the field, and the gold standard may be some time-consuming or expensive tests done in a laboratory. So how do we get the clinical results to compare to the gold standard that we set from the detailed, expensive lab test? Well, that's what our screening or diagnostic tests are about. And how good the test is, one way of assessing as we're trying to select which test to use, are sensitivity and specificity. Sensitivity, if I want to make sure I identify all of the disease people, sensitivity plus specificity equal to 1. So when I say gold standard, that's the thing we use as we're creating our test. The gold standard is what we use to evaluate how good our test is. Is it not healthy plus non-healthy equals 1? Healthy plus non-healthy equals the total. But you're missing something. All we know is our test result, and that's what sensitivity is. We don't know the number of healthy people. All we know is our test result, and that's what specificity is. Let's do it again. Basic idea, there's numbers, there's reality, and they're not the same thing. The whole point about this conversation is not that we, in a godlike way, can reach out and know who the healthy or non-healthy people is. So sensitivity plus specificity should be 1. Let's do it again. I'm repeating myself here. I want you to recognize it's possible for sensitivity to be 100% and specificity to be 100%. It's possible for sensitivity to be 100% and specificity to be 0%. Do you follow me on this? Because we're not talking about what is, we're talking about ability to find what is. It's possible great at finding disease, but we're terrible at finding healthy people. It's possible great at finding healthy people, but we're terrible at identifying disease. It's not about what is, it's our ability to find it. If a patient asks how sure we are of their disease, that's a great question. I haven't addressed that yet. We're going to go there next. Hold on. You're asking about something called predictive value, which is different. All we're talking about in sensitivity and specificity is selecting the test we're going to use. What we're going to say to the patient clinically is a whole nother conversation. Decide to use sensitivity or specificity, you calculate them from the available data. Remember, in all of our conversation, the 2x2 table preceded everything. First, we put in place the 2x2 table. First, the table that lays out the correspondence between the test and reality, which I've been calling the gold standard. And then we get to ask our questions using that given data. Remember, we don't get to see reality. We get to look at the test results. And isn't it pretty important to get a sense of how good that test result is? We have an 85% hit rate for detecting disease, and we have a 65% hit rate in this particular test for identifying the healthy people. We're better at sensitivity and worse at specificity. That's how we're going to select the test we're going to be using.